Hello everyone. My name is Sergey Shilukhin. I am a software developer with Hortonworks, working on Apache Hive. And today I'm going to talk about LLAP, which is a new large performance feature in Hive that we are doing in Apache Hive. LLAP stands for live long and prosper, or live long and process. Some people might tell you that it stands for Low Latency Analytical Platform, which is also true, but it's a backronym. So the title of this talk is not as impressive as it should have been. If it said LLAP sub-second queries in Hive, that probably would get more people to join, but unfortunately I chose a technical title which describes what LLAP is, but doesn't describe why we are doing it and what it does. So, as I've said, this is a beginning that we hope to bring about in Hive performance, and we're hoping to get the Hive queries for interactive use cases to run in sub-second. So this talk is going to be fairly technical. I'm going to give an overview of what LLAP is and why we are doing it. Then I'm going to deep dive into the aspects of query execution with LLAP and the technical details. I'm going to provide a little bit of preliminary performance results, and I'm going to give the current status and when you're going to be able to use it and how. So to recap, in 2013, Stinger initiative was launched in Apache Hive to speed up Hive query performance. It was delivered in 2014 in Apache open source, and it was followed by Stinger.next initiative, which is currently in progress, which is supposed to bring enterprise SQL at Hadoop scale. Some parts of the Stinger.next initiative, such as cost-based optimizer, have already been delivered, at least in some form. And altogether, over those years, Hive has went from, so to speak, from glacier interactive to human interactive, from like queries running for hours to queries running for seconds, which is good. The question is, what is the next step for Hive performance? So if you look at the next step, the first thing that we notice is the container model that Hive currently uses has a lot of drawbacks. First of all, the startup costs, especially we all here know and love Java and all it brings with it. The startup costs for JVMs, the initialization costs for JVM become a significant bottleneck. Java also has some nice features like just-in-time optimization and inlining, which doesn't work very well when all your processes go away in 2 seconds. Also, when you're running lots of little processes on a machine, you don't have a lot of opportunity for either sequential sharing, which is known as caching, or the actual sharing of data between the executing processes. I mean, you can do it, but it has its own complexity. And in addition to container problems, we also notice that there are some I/O problems. Traditionally, the Hive queries are processing bound, but as the processing time improves, we notice that some queries become I/O bound. And it's actually especially bad given that currently in Hive, I/O is actually done sequentially with processing. So you ask for some data, you get it, you process it, etc., 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 which is not very good. So what's the answer? As far as we are concerned, we saw that most of these problems could be solved if we were running the processing in a daemon, which is not a new idea in the database world or big data world. But we also want to preserve the existing benefits of keeping Hive flexible and allowing it to support huge workloads, ETL and stuff. So we are proposing a hybrid execution model which will have both daemons and containers. Some small queries may run entirely in the daemon, some very large queries may run entirely in the containers, and maybe a combination of the two. So immediately you see that all the problems that you had on the previous slides turn into solutions, because now we don't have the startup costs, the just-in-time optimizer has time to optimize, we can introduce a cache into the daemon, we can share data into the daemon, etc., etc., etc. So we started working on this. We submitted the design document to the community in about fall 2014, and we started to work in earnest in January 2015. So right now it's been half a year, so we have something that we can show. So to facilitate the usage of the daemon, I forgot to say, to facilitate the usage of the daemon from Hive and from other places, the daemon is going to use query fragment API. And by query fragment, we mean a small piece of executable small piece of computation that you can run on a single machine, and you can basically have some inputs, some outputs, and some operations to do on those, and then you can build these query fragments together into a query, just like in a regular container-based DAG. So first, I want to make some clarifications in advance of what LLAP isn't, because there is potential for some confusion. First of all, LLAP is not an execution engine. It doesn't replace Tez, MR, or Spark. It can be used by an execution engine as a service. So you can basically have some work offloaded to the LLAP daemons to be done faster and better. It's not a storage layer. It doesn't store its own persistent data or do replication. It actually reads the data from existing sources. So basically what you're talking about here is kind of like a relational view of a data node. The data node, in case of HDFS, still stores all the data and takes care of all the storage layer consideration. And as I've already said, it doesn't supersede Hive, which is actually, I think, is a key point, is that depending on the query requirements and the data sizes and the workload types, you can run in containers, in the daemons, or in a combination of the two. So here's an example. Actually, I'm going to be pretty brief. You go from the MapReduce, which you all know and probably love, or not, to optimized graph in Tez, which here is the same exact graph minus HDFS, but it could actually be also a different optimized DAG. And then we go to LLAP, which could be also the same DAG or a different one, where some of the computation is loaded into the daemon. How do you run those guys if you want to use them? So right now you cannot use them, unfortunately, because it hasn't shipped yet. But when it does, what will be able to run those in your existing Yarn cluster using Apache Slider, which is an Apache project that helps you run long-lived services on Yarn. It makes it easy to start, tear down and flex your clusters, and maybe even share them. And right now, the resource management there is not very flexible. You have to decide in advance how much resources to allocate to LLAP, but in future, we are going to work with Yarn delegation model to make it much more flexible for diverse workloads. Obviously, if you have a daemon, everything suddenly starts looking stateful and persistent. So we start thinking about some additional benefits we could realize in the future, such as obviously security comes to mind. You can enforce access control at one point, and because LLAP is aware of the columns, and unlike of data node, obviously, you can actually enforce access control on column level. You can enforce priority for concurrent workloads. You can do improvements for Hive transactional functionality. And you can also provide an IP to make it a one-stop shop for relational view of the data for other frameworks, not just Hive, for example, Peak, Spark, or Cascading, etc. But those are all, right now we are focusing on the performance aspects of LLAP. This is work in progress, which will be realized in future stages of this. So I'm going to start with very briefly with the query fragment API. It doesn't make any sense. Well, it doesn't make a lot of sense to go into details right now because it's still in early stages, so we haven't finalized it. It will be finalized when we ship it. You will be able to submit query fragments to LLAP daemons. Query fragments consist of input channels, output channels, and the physical algebra to execute, plus some attendant things like metadata or maybe some stats for local optimization and stuff like that. The channels are pretty important because we expect the data to be, the input and output data be potentially large from the operators, so the data will be returned asynchronously. You want to basically talk to LLAP like you talk, for example, to HBase, like ask for something and get it back. You'll have a channel where the data will stream and will potentially be used by other daemons or some other execution objects like containers. I won't dwell a lot on algebra. It will have your standard operators like scans, filters, merge joins, hash joins, etc., 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 and all the expressions and data types that you come to expect from the typical Hive query execution. And the client library will be provided for easier work with streams and for easier submission of query fragments. Now, the main part of this talk is mostly about the technical details of LLAP. I'm going to start with query execution. So when you submit the fragment using the API to the daemon, what happens in the daemon and how it all works in the existing implementation. So for now, we are building the support for LLAP into Tez. which is already the most performant Hive execution engine. And the features are being added to test to be able to work with external systems such as LLAP. They're generic in implementation, but we're using them to work with LLAP daemons and delegate the work. Note that the high-level features like compilation and DAG coordination remain almost completely unchanged, and the operator pipeline in Hive also remains mostly unchanged. What changes is how you run the operators and the low-level I/O below the operators, which is what we are targeting, and also has advantages of preserving all the Hive functionality as is, so we don't lose existing benefits that Hive provides. There are several ways to decide where some things will run. You can run nothing in LLAP or in LLAP if you want, and that will obviously be pretty boring. You can run everything in LLAP, which is an option and that actually works for most queries. Or you can use an intelligent policy to decide, which is called auto mode. It basically runs based on the data sizes, data sources, and the work type. One thing to know that in any mode, LLAP is not going to run user code such as user UDFs, at least for now, mostly for security reasons. It's possible to add the functionality to run blessed user code in the future. But yeah, for now, user code has to run in the containers, which provide much more strict isolation for this. So you go from the existing DAG executing on a cluster to auto mode, where you have some mappers and maybe one chip reducer sent to LLAP and one reducer executing in AAM. In this case, which is also a possibility for like last stage of an aggregation, which can be very small. And or you can have in all mode where everything is executing in the daemons. So right now, TES uses greedy scheduling for LLAP. It basically schedules assuming nobody else is in the cluster, as it usually does with, nobody else is in the cluster, and the daemons figure out which fragments from different queries to schedule in which order. For that, we have a number of executors in the daemons. When you submit a fragment to the daemon, you can have several outcomes. It can be accepted and assigned to an executor. It can be rejected, which is basically a cheaper version of not getting a yarn container because your cluster is too busy. Or it can be queued. If it's rejected, TES is going to reschedule it to a different daemon which is not so congested, or maybe wait if all the daemons are congested. The queue is a trade-off between throughput and latency. Obviously, it's good for throughput to have the fragments available to execute immediately after the previous one completes. On the other hand, you probably don't want for latency for your fragment to wait for a long time. So it's a trade-off. You can configure it, and right now we're trying to tune it for the short-lived queries. So if you're running a fragment of a small query which has a small number of tasks that are going to finish fast, they're going to be run faster than the fragments of a large query which is wide and is going to take forever to run. So one thing that queue allows you to do better, and the daemon with central state allows you to do better than yarn container, is preemption. If you have a very large query, say an ETL query, and it's taking up some slots in the cluster, and many of those queries use pipelining, so a reducer would be running while the mappers are still finishing and preloading the data. That's good for ETL query, it makes it run faster, but on the other hand, the slot is taken, so your interactive queries perhaps cannot run. In that case, we distinguish between finishable and non-finishable query fragments, ones that have their inputs and ones that don't have their inputs yet. And in case the fragment is not finishable and we decide that some other query might finish faster if we kill it, we might just terminate it and preempt it with a different fragment, which will basically allow your interactive query to finish faster. This is only a beginning of the scheduling work that you can do on a daemon and globally for parallel queries, but this is already a pretty good start. So when the fragments run inside the LLAP daemon, they can gain advantages of certain I/O and other low-level improvements. First of all, as I said, the current situation with I/O in Hive is mostly synchronous. So you ask for some data, it's read, it's decoded, as some people have mentioned in best practices talks here. Deserialization in Hadoop is expensive and decompression is expensive. So that is true in this case also. And then you process the data, and then you go for some more data, and then maybe it's decoded or read from HDFS, etc., etc. And while HDFS is pretty fast, especially the remote reads can be slow, and even the local reads can sometimes be slow. So we have a very simple feature, well, relatively simple feature to deal with that. It's called IO elevator, which basically means that we offload IO decompression and decoding into a separate thread pool, which means that you can process the data while the other thread is reading the data and decompressing the data, which is good if you have many cores, or if you have basically just if you're reading a lot of data and processing it. So that speeds up queries by itself. It also opens up a road. Note that it's a common theme in this talk that this feature opens up a road to many new improvements that we can realize that we haven't yet, obviously, in 6 months. But this opens up a road to such things, the local I/O optimization, such as, for example, spindle-aware I/O, which is with like 5 containers running on a node and reading whatever they want to read, is pretty much impossible. There is also such a thing as caching. We basically cache off heap the data that we have decompressed from the disk file, from the HDFS files. Off heap is to alleviate the GC problems on the daemon, and we use pluggable policies to decide which data to evict. The cache, fortunately or unfortunately, is a trade-off, again, based on the workload between so if you cache something in memory, you take space away from operators. So like sort buffers, map joins, group bys take a lot of memory. So the question is how many pipelines do you want to run in parallel versus how much data you want to cache. And depending on your workload, you will have to, you will need to tune the cache accordingly. However, as Hive operators become more efficient, it becomes better to cache than not to cache. For now, we have to say we're running with small cache mostly. One good part of the cache that's working for most workloads is a metadata cache and index cache for predicate pushdown. So if you're running a query with a large data set which is highly selective, in some cases we have observed that it can run almost without touching HDFS on most of the nodes, because all the indexes are cached, so it can look at the indexes and say, oh, I actually don't need anything from here, or like I only need a little bit, so I will just read this tiny bit of the file, instead of doing the disk seek for every file and then every fragment of the file and then reading all the metadata and parsing it. So that's helpful. You can also share hash tables for map joins. You can share plans for the query fragments from the same job, so you don't have to deserialize them multiple times. Again, deserialization is expensive. You also get much better use of JIT optimizer. If any one of you have used tests with container use, you might have noticed that if you run queries repeatedly, they become much faster. Well, if you run several queries in a row, the further queries become much faster. Part of it is due to just-in-time optimization and aligning. So previously, you obviously needed to have containers in your session to do that. Now the daemons are there, available for everyone, and you can get the same benefit for, well, not for free, but much cheaper. So that brings me to the performance numbers. We run the performance tests on a relatively small cluster compared to what we normally run performance numbers on. We run interactive queries of TPCDS because our main use case is interactive. I have also run personally large queries, and they do run and they run faster, but we don't have them here, unfortunately. We are using Hadoop 2.8 because it has some performance improvements for concurrent reading. We're using Hive Server 2 and Test 0.8, which is the latest yet unreleased version. And we are comparing the latest release of Hive, which is 1.2, versus the alpha, the pre-alpha, I would say, release of LLAP, which is currently in a branch. We haven't done a lot of tuning for LLAP except for making the cache smaller, because, as I said, right now the operator pipeline in Hive is mostly processing bound, not IO bound. And yeah, so for tests we have used pre-warm and container use. So I have to know that this is early stages, this is alpha, but we already see some improvement for queries. Interactive queries run about 1.5 to 4 times faster, depending on the query. One big benefit is the first query time. First query time improves significantly, especially if you consider the scenario with tests without pre-warm. Pre-warm does make first query run pretty fast in tests also. And parallel queries have some improvement. Well, one thing we did notice with parallel queries is that there are, in the libraries we use, there are lots of logs. People are apparently fond of epic logs. So they're all ripe for removal, and we'll hopefully remove them or work around them, and parallel queries should be much faster in short order. So let's get to the numbers. These are the numbers. I don't really have much to say here. As you've noticed, some queries have become maybe 30% faster. Some queries have become 4 times faster. Actually, in some queries, if you see in this cluster, the compilation time of the query is now a significant amount of part of query execution. So maybe that's something we'll work on next. The search never ends. One thing though is that, again, I have to reiterate, this is an alpha release. We didn't really do a lot of perf work on it. So we just implemented all the features, did the basic perf work, and here it is. With parallel query time, there is a little bit of improvement over TES, but obviously we are going from a different baseline too. So instead of with 4 executors on Hive Server 2, that's not the same as LLAP executors. Those are basically the parallel queries running on Hive Server 2. We went from 50% to 40%, well, 41% technically, of serial time of execution. Obviously, to start with, the total execution time is only half of what it used to be. So that's a pretty good improvement. We do know we have a lot of work to do in parallel query execution, but this should be much easier with the daemon and the state that the state and ability that it provides compared to the previous model. So we're pretty sure we can get this done. Which I guess brings me to the current status of the product. As I said, we started working on this activity in January, and right now we are at alpha stage, where we are going to release a community technology preview pretty soon. We're fixing the bugs. Once the bugs are fixed, we are going to probably publish a blog post. We are definitely going to send a mail to an Apache Hive mailing list as soon as we merge the branching. So you will be able to look at it and play with it and use it to some extent. We have all the basic features functional. We are restricted currently only to running on TES and running the I/O parts on vectorized or ORC format, which is the fastest Hive that already exists. Sorry, I couldn't resist. There's lots of performance improvements not yet realized, both just low-level profiling and figuring out what takes time, and just high-level architectural features, like, for example, better handling of high contention on a daemon, which is right now is just queue and preemption. There's lots of stuff that can be done there. And all the features I was talking about that are fairly advanced are still mostly in work-in-progress status. So our current work in progress is the performance work, the concurrent query work, and we are also going to define the API, which is pretty important in order to allow probably more use cases from the community, and potentially integrating with other products in order to make to basically account for other scenarios and other use cases. It's probably also going to be important for our features that we're going to work on later, such as security and column level security. We have already had some interest in working, some like other people in the community working with us on security. Unfortunately, we weren't able to reciprocate very well due to the flux and the chaos of working on alpha release of a product. If you're in the audience, we'll get back to you. I'm sorry. So yeah, security is our top priority, obviously, because enterprise SQL cannot exist without security. And from other features, we have a whole bucket list of features, starting from performance features, like, for example, interleaving of execution instead of preemption, where you don't lose work, to like more closer features, like, for example, ACID improvements and stuff like that, to pie in the sky features, like, for example, temporary tables in LLAP. So yeah, this is about all that I have. If you guys have any questions, we have a lot of time. Mm-hmm.
Concurrency execution for those operators should be also good, right? So I mean, like the vectorization and arc, and you want using the batch execution for those like pipeline operator to execute.
Yeah.
So is that possible? Like we move that feature out from LLAP to, some deployment probably we cannot benefit from, we cannot use the LLAP, but that feature seems like improve the whole execution performance.
Do you mean the preemption feature?
Which one?
Which feature?
The concurrency execution for the operator, the batch operator, the vectorization.
Oh yeah, so the features like vector improvements to vectorization will be available obviously just in regular Hive operating pipeline. As I said, that doesn't change a lot. So that will be available in container-based execution. However, many features for concurrent query execution, you cannot really do them without having a central view of what's going on the node. Like, for example, sharing data. You cannot, well, it's possible, but it's not. It's pretty hard to share, for example, a map join hash table between different processes running on the same node with different runtimes without having a separate central process to coordinate it. So that's one of the reasons we are doing this, is that many of the concurrent features only become possible or easy to do if you have a central state, if you have like a central persistent state. So some will be, some won't be, yes.
I have a question. What happens if the LLAP daemon fails?
Presently, we are using slider functionality to deal with that. Slider provides built-in. You mean the entire daemon fails and crashes?
Okay.
So or do you mean? Sorry, yeah, I have to clarify the question. Do you mean the entire daemon fails or the task fails?
I mean the tasks, and maybe I think if I understand correctly, the test will connect to the LLAP daemon, right? No?
Yes.
Yes? Okay, so then the client need to be aware of the failure, I think. So what's happened?
So the test, yeah, so if the task fails inside LLAP daemon, the daemon will basically send back the regular status update back to the whoever submitted the task, in this case TES, to indicate that the task has failed, and it will the TES AM will deal with it just with a regular, like with a regular container filer. When you're submitting a query fragment to an executor, you can think of this like executor and query fragment combo as like a mini container, basically a container running inside a process instead of running the entire JVM with everything. So it will be handled the same way. Okay. If the daemon fails, we'll use the basically using slider to restart it and the registry to find it.
So basically, it's LLAP daemon is stateless, right?
Yes.
Okay.
Yeah, it's all the daemons are stateless.
Okay, thank you.
Yeah. Oh, anyone? Yeah.
What is the approach? Can you describe the thought process behind how do you choose which data to cache and when to evict it from cache?
We cache all the data we read currently, and we evicted when the cache is full based on a certain policy. The policy is pluggable. Right now we have first in, first out, which is the best cache policy ever. And we have least recently frequently used, which is based on a research paper, which is also a local policy. However, some research papers that I've recently read by Microsoft, I think, has a very good argument for basically input-aware cache policies and centrally coordinated cache policies, which is something that we might do in the future, where you basically, if you have like a data warehousing application, your dimension tables will be cached and your fact tables will mostly not be cached. Because they are large, they're not going to fit there. They're not going to fit in the cache. One thing that's cached with high priority is metadata. So metadata, in most cases, if it makes it to cache, unless you don't use it for a long time, it's going to be in the cache. Yeah, so we don't evict data actively. We evict it using just like the industry standard, so to speak, cache policies. Yes.
So you only cache an entire table. You don't do a sub-table caching?
We cache, the cache granularity is a column chunk. We basically cache the columns based on the way they are stored in a file. And for each column, we cache like a segment of data.
And the follow-up question, you cache the data decompressed or compressed?
We cache the data decompressed, but still encoded.
Okay.
We found that we actually had a prototype a little bit earlier where I was trying to cache the fully decoded, basically the ready to process data with a view of operating on the data directly in cache without any copies. But that is a very far-fetched feature in Hive right now, so we just went to caching the encoded data. Yeah. Yep.
So seems like this is optimized for ORC formats, right?
This is I would have to like so there are two aspects. First of all, this is optimized for columnar format. That is definitely true. Because obviously we are trying to deliver something as fast as possible. We are working with ORC format, which is familiar to us, and as far as we are concerned, is the best format. But there is no reason why one couldn't add, especially when the code is more mature than now. It's not like sitting in a branch somewhere, but actually merged into Hive trunk. There is no reason why Parquet format or some other format couldn't be added to it.
So two more questions. What percentage of your customers use ORC versus CSV? Because while ORC is very performant, I agree.
Yes.
Most customers still prefer to use CSV because they have to export it out. And second question, is CSV in your roadmap?
So first of all, oh yeah, sorry, one more thing I forgot to mention about ORC. You can still run the tasks inside LLAP daemons and get the benefits of that. You just won't get the benefits of the I/O part if you're using non-ORC format or non-columnar format. We don't have other formats, non-columnar formats on the roadmap, but it is conceivable that we can add it or somebody in the community can add it. But I do have to say that for most workloads, it's good to use ORC or some other columnar formats. The only type of workload where you might want to have non-columnar format is the ones where you most of the time you read all the data, in which case columnar format is actually slower. But again, I mean, I wouldn't, unless it's compressed CSV, I wouldn't use CSV in this case, but yeah.
Do you know the percent breakdown?
Excuse me?
Percent breakdown ORC versus CSV that your customers have? Maybe?
Oh, I don't have these numbers handy, I'm sorry.
Question about bucketing sorting and whether there's any kind of support to do anything smart around, merge joins or, kind of low-level storage merge preserving the sort of a different data set or bucketed sorted tables.
We have no special functionality for that as part of LLAP right now. If you actually talk to this guy in the second row, his name is Gopal, he knows everything about that, he can tell you.
It's been really difficult to get bucketed sorted merge join to work in Hive in general, but yeah.
Yeah.
That's somewhat.
I'm sorry, Gopal. Okay. Oh, yeah, delegation. Okay. Oh.